Okay, let's continue. Example 2, a falling object continued. Suppose that, as in example 2 of section 1.1, we consider a falling object of mass m equal to 10 kilograms and drag coefficient gamma equal to 2 kilograms per second. Then the equation of motion 1 becomes this equation. Let me try to figure out or try to find the motion 1. Motion 1, I think, oh, okay, this is the motion 1 equation. Let me put it here. This is the motion 1 equation. Then the equation of motion 1 becomes let me write it down firstly. Becomes this dv over dt equal to 9.8 minus v over 5. This is equation 21. And because here we say that m is equal to 10, so this is 10, and gamma is equal to 2. So basically this will be 10 dv dt is equal to, and g is equal to 9.8, so minus 2v. And then we just divide this equation on the left side and on the right side at the same time by 10, and then we can get this equation. Okay, continue. Suppose this object is dropped from a height of 300 meters. Find its velocity at any time t. This means find v of t. How long will it take to fall to the ground? And how fast will it be moving at the time of impact? Solution. The first step is to state an appropriate initial condition for equation 21. The word dropped in the statement of the problem suggests that object starts from rest, that is, its initial velocity is 0. So we will use the initial condition v0 is equal to 0. Okay, this is, let me write down first. V of 0 is equal to 0. This is the equation 22. And basically the setting is this is the object, and we drop it and to the ground, and here is the height is the 300 meters, and v of 0 is 0. The solution of equation 21 can be found by substituting the values of the coefficients into the solution 20. Okay, let's find the solution 20. Here, equation 20 but we will proceed instead to solve equation 21 to solve equation 21 directly. Now first rewrite the equation as this 23. This means we rewrite this equation 21 to the equation 23. Okay, let's write it. 23 is dv over dt over v minus 49 is equal to minus 1 over 5. This is equation 23. Basically, the principle is that we hope the variable v is going to on the left side of this equation. So we can do it by maybe we can do it first by factoring this term and then divide this term by something. Let me show it. Maybe we can firstly factor this coefficient. If we factor 1 over 5, and here will be minus v, right? And then we factor 1 over 5. So what number is here? The original number is 9.8. And if we multiply by 5, so when we expand this bracket, this term will become 9.8. And anyway, we can do this transformation or factoring. And then we just directly write the result of this term. 9.8 times 5 is this is 49. So it will become this expression. And then in order to put the variable v into the left hand side of this equation, so we just divide it by 49 minus v. But here, if we just do another transformation, we let the v in the first order and 49 in the second order, we just give it a minus sign. That is minus 1 over 5, and here is v minus 49. So these three expressions, they are all equal to each other. And now we can just divide by this term. So it is, and then lastly, we can get dv over dt divide this v minus 49, and it will be equal to minus 1 over 5. This is equation 23. By integrating both sides, we obtain equation 24. By integrating, let me write it down first. Equation 24. Now v of t minus this absolute value is equal to minus t over 5 plus big C. This is equation 24. So similarly, maybe we have do the antiderivative in the in the before examples. So it's the same. It's about the noun. If we have to know some basic formula, but how to start? Usually, I write down the basic formula first. That is noun x. If we do this derivative, it will be 1 over x. So here, similarly, maybe we can think maybe x is equal to v minus 49, and we substituting this term, that is d ln v minus 49 absolute value, and here we should be write down the dt because v is a function of t, and it should be, we use the chain rule, it should be this v minus this outer result, and then times the inner result is dv this and dt, and this term, I mean this term dv minus 49, the result is dv dt. So you can see this term over dt is equal to this expression, and this expression is exactly this expression. And now we want to calculate its antiderivative. So the result is this thing, because this term's derivative is this. So this antiderivative is this, right? Anyway, we can get the antiderivative is this, yes, and this is the left-hand side antiderivative, and the right-hand side antiderivative is just minus t over 5. Maybe we just do the quick verification, because to calculate its derivative is minus 1 over 5, and here is another constant. So this is equation 24. And then the general solution of equation 21 is the general solution of equation 21 is, so this is just, we continue to do this calculation, because here just some relation equation, but eventually we want to know what is v of t, so we just continue to do. What is v of t? Just do the exponential calculation, e ln v of t minus 49. The left hand side do the is power of ln of this term, and right hand side also do is power of this term. And by the definition of ln, we can get this whole expression is the value of v of t minus 49. This is equal to, and this is the same, but we can write it this way, times e big C, and then we remove the absolute value, so is plus or minus, and then we exchange these two terms order, E big C times E minus T over 5. And then we let this thing, we use a small c to be equal to its value. And then we move this term to the right. We can get, let me use the black, we can get Vt is equal to 49 plus small c times e to power of minus t over 5. Okay, this is equation 25. Where constant c is arbitrary, to determine the particular value of small c that corresponds to the initial condition v of 0, we substitute t is 0 and v is 0 into equation 25, with the result that c is equal to minus 49. So now if t is 0, and here t is 0, and v of t is 0, I mean here is t is equal to 0, t is equal to 0, and v is equal to 0. And we can get 0 is equal to 49 plus small c e is minus 0 and 5. And then we can get this 0 is equal to 49 plus this whole term, the value is 1. So lastly, we can get c is equal to minus 49 here. Then the solution of the initial value problem 2122 is, yes, now we just put the c's value into this position. We can get v of t is equal to 49 plus minus 49 times e to power of minus t5. Or maybe we just factor the 49. We can get 49, and here the remaining value is 1, and here is remaining minus. Yeah. So this is the equation 26. Equation 26 gives the velocity of the falling object at any positive time after being dropped until it hits the ground, of course. So before the object hits the ground, this equation is valid, it's correct. Graphs of the solution 25 for several values, and this is a general solution, are shown in figure 1.2.2, with the solution 26 shown by green curve. It is evident that regardless of the initial velocity of the object, all solutions tend to approach the equilibrium solution. Vt is equal to 49. This confirms the conclusions we reached in section 1.1 on the basis of the direction fields in figure 1.1.2 and 1.1.3. To find the velocity of the object when it hits the ground, we need to know the time at which impact occurs. So when this object hit the ground, in other words, we need to determine how long it takes the object to fall 300 meters. To do this, we know that the distance x the object has fallen is related to its velocity v by the differential equation. V is equal to dx over dt. V is equal to dx. So here we just add the assumption or the condition by default is v of t is equal to dx over dt. Here x is the distance, and then we substitute this term into this position. We can get dx over dt is equal to 49 1 minus e minus t over 5. This equation 27. Consequently, by integrating both sides of equation 27 with respect to t, we have. So now here this is a derivative. We want to do antiderivative, or namely integration. So basically dx dt is antiderivative is x, right? If we think of the function x and then we do dx over dt, so it is equal to dx over dt, right? And now we want to do this terms, its antiderivative. So the result is this x, because x its derivative is this, so this antiderivative is x. So when we do the integration on the left side, the result is x. The result is x. And we consider the right side. What's the antiderivative of this right hand side? So maybe it's a little complicated, but what we do at first is to try to guess its results, guess some function. How about let's start from this e's power of minus t over 5. We try to calculate its derivative, d this and dt. it's we use a chain rule. The basic formula is that each power, the derivative is also itself. So the first part should be itself, and then we do the derivative of this term. The result is minus 1. So here is the dt. So its derivative is this thing. This function's derivative is this thing, right? And now we have this term. So we want to construct this term into this side. So maybe here is minus 1 over 5. Maybe we try to cancel out this thing. So we multiply. We try to multiply minus 5, and here is also minus 5. And on the right hand side, it becomes this thing, right? And the left hand side, it can be changed to, we put the minus 5 into this function. It's d minus 5 times e over t. Yeah, this dt. So now we can get, if a value, a result is here, we calculate the derivative of this whole function. The result is here. And if we want to do this thing, its antiderivative, the result should be here. And now we can try to write down the antiderivative of the right hand side. The 49 should be the same, and 1 can be the same, and minus, and this thing's antiderivative, antiderivative is minus 5 times e over t over 5. But remember, when we do antiderivative, we need to add a big C term, because there are many possible C's values. So the right hand side, its antiderivative should be this expression. We can verify whether it is correct. If we calculate the derivative of this expression, it should be, the derivative of this expression should be 49, keep the same. And this 1, okay, there's some error because one's derivative is 0. So maybe here should be 1 times t. 1 times t is okay. So and now we continue to calculate the new derivative of this new expression. The 1 times t is derivative is 1, and here is minus. And the c derivative, because it's constant, is 0. And this thing minus 5 times e to power of minus t over 5. Its derivative is this. So it's e minus t over 5. So now we can see that, just continue to simplify this term. It's also equal to 49 1 minus e minus t over 5. And it is exactly equal to this term. So this thing is the antiderivative of of uh, of this thing. And now we can write down the both sides their antiderivative, which is x equal to this 49 t, and we do simplification here. 49 t, this minus minus will be plus, and 5 e minus t over this, and this minus c or plus c, it's both okay. Maybe we just continue to keep this the same c, so it's minus, this is minus big C. Okay, now so where are we? 27. And on the textbook, the equation 28 is this. X is equal to 49 t plus 245 times e minus t over 5 m plus, here is a small k. Okay. And we just expand this bracket times 5 is 245, and this 49 times minus c, we can let k be 49 times minus c, and we can write here, yes, where k is an arbitrary constant of integration. The object starts to fall when t is equal to 0. So we know that x equal to 0 when t is equal to 0. From equation 28, it follows that k is equal to minus 245. So what's happening here? Because we use a condition, it's the initial condition. Here, when t is equal to 0, x will be equal to 0. And we insert this value into equation 28, we can get 0 is equal to 49 times 0 plus 245 times e minus 0 m plus k. And then we can get this thing is 0 and this term is 1, so this 2 and this k. Yeah. So next we can get k is equal to minus 245. So the distance the object has fallen at time t is given by, and then we just substitute the k's value into equation 28. We can get x is equal to 49t plus 245 times e minus t over 5 and minus 245. This is equation 29. Next, let t be the time at which the object hits the ground. Then x is equal to 300 when t is equal to t. By substituting these values in equation 29, we obtain the equation. Because we want to know how long the distance is 300, right? So we just let the distance be 300, and we want to figure out what's the value of t. So this is maybe the the 49t plus 245 e minus big T over 5 minus is this is equation 30. Here it just exchange the two sides of this equation. You can see here is and then this thing become here in the big T. The value of T satisfying equation 30 can be approximated by a numerical process. A computer algebra system provides this capability. Many calculators also have built-in routines for solving such equations using a calculator or other computational tool, with the result that t is approximately equal to 10 seconds. At this time, the corresponding velocity vt is found from, let me write down. Suppose we use some computer or program, we can get this t is approximately equal to 10.1 seconds. At this time, the corresponding velocity vt, we can go back to use the solution we have at the early time and insert the t's value here, and then we can get v of t. And so we can get v of t or v subscript t is approximately equal to 43.01 meters per second. The point tv is also shown in figure 1.2.2. This is the tv point. And next, further remarks on mathematical modeling. Up to this point, we have related our discussion of differential equations to mathematical models of a falling object and of a hypothetical relation between field mice and owls. The derivation of these models may have been plausible and possibly even convincing, but you should remember that the ultimate test of any mathematical model is whether its predictions agree with observations or experimental results. We have no actual observations or experimental results to use for comparison purposes here, but there are several sources of possible discrepancies. In the case of the falling object, the underlying physical principle, Newton's laws of motion, is well established and widely applicable. However, the assumption that the drag force is proportional to the velocity is less certain. Even if this assumption is correct, the determination of the drag coefficient gamma by direct measurement presents difficulties. Indeed, sometimes one finds the drag coefficient indirectly. For example, by measuring the time of fall from a given height and then calculating the value of gamma that predicts this observed time. The model of the field mouse population is subject to various uncertainties. The determination of the growth rate R and the predation rate K depends on observations of actual populations, which may be subject to considerable variations. The assumption that R and K are constants may also be questionable. For example, a constant predation rate becomes harder to sustain as the field mouse population becomes smaller. Further, the model predicts that a population above the equilibrium value will grow exponentially larger and larger. This seems at variance with the behavior of actual populations. See further discussion of population dynamics in section 2.5. If the differences between actual observations and a mathematical model's predictions are too great, then you need to consider refining the model, making more careful observations, or perhaps both. There is almost always a trade-off between accuracy and simplicity. Both are desirable, but a gain in one usually involves a loss in the other. However, even if a mathematical model is incomplete or somewhat inaccurate, it may nevertheless be useful in explaining qualitative features of the problem under investigation. It may also give satisfactory results under some circumstances, but not others. Thus, you should always use good judgment and common sense in constructing mathematical models and in using their predictions.